Bismillahirrahmanirrahim. Last time we started chapter 4, or chapter 4 may we saw the bending, right? That is the pure bending. We started with the last time we started with the chapter 2, we revised chapter 3, and then we come up with this section of chapter 4 in which I demonstrated that if I have a beam having a uniform cross section and I applied a moment, in this particular case moment z about z axis, so bending will be in xy plane. Likewise, if I apply the moment in y plane, so in the y axis, so bending will be in xz plane. So I have physically demonstrated all this in my last lecture as well. So when I apply the moment about z-axis means mz, if you look over here, so you can categorically see that we have a compression inside of the curvature, whereas a tensile or the elongation along the outermost boundary, right? So this is basically the curvature. This one is basically the curvature one, right? You can say this is the curvature. And if I go for this one, so just a minute, right? So now there is no angular deformation involved, so we will consider only the normal stresses, resultingly normal strains. So we will be dealing with these sigmas and epsilons and dels. Since inner side is in the compression, outer side is the tensile or the elongation. So inner side compression is always in the normal stress value. We generally consider compression in a negative and the tensile is a positive. So we are moving from negative to positive, right? So there must be something where no stresses will be there, resultingly no strain will be there, and that surface is called neutral surface. Over here you can see this is the neutral surface, and this neutral surface is along the longitudinal plane. This is our longitudinal plane, this one is our longitudinal plane, and this is our cross sectional area. Along the cross sectional area, this neutral surface is called neutral axis. So the distribution of the stresses from negative to positive, from compression to the tensile force, is around the neutral axis, or neutral axis has practically no stresses on it, no strains on it, right? And we defined later on in the slides as well that this basically has the neutral surface is the surface about which compression and tension is going to happen, right? And then we saw that if we have a uniform cross section like this one, how I'll go downward. So now if I have a very small area dA over here, dA over here, dA over here, and that is existing at the distance y from the neutral axis, right? So one force will be going in because this topmost surface is in the compression and lowermost surface is in the tension. So stresses will be going in into this one and will be coming out from this one, right? Since the forces are equal and opposite, so sum of all the forces will be equals to 0. But sum of moments will not be equal to 0 because they are creating the moment in the same direction. So we cannot make them nullify. See, so there will be a very small amount of the moment that will be existing because of these compressive and the tensile forces, and that moment will be causing the bending, right? So sigma a over here is d over df over a, dA, and df, a small force that is being applied on this area, is sigma dA. So we further use this somewhere in the slide. So now we come on, this is just the revision we did from the last one, and now I'll come up with the with this one. the slides one, right? So we will quickly revise the slides so that you can have an idea what we did last time, right? So we started with this example over here, pure bending, right? And then we went for the eccentric loading, and we saw whenever there is eccentric loading, there will be a equal and opposite force, but that force will be causing the some moment over here, like uh, so this force will be this eccentric loading will be causing the moment over here as well. Then we went for the transverse loading, and we saw that this transverse loading, that loading that is vertical to the longitudinal plane. This is a longitudinal plane, and this P force is vertical to it. So this is the transverse loading, and transverse loading always called a transverse shear, B, P dash, and a moment as well, right? So in this chapter, we don't consider this one transverse shear, or the bending shear we used to call it. We will deal in the chapter 5 in it with this, right? So here we are ignoring this one. Ignoring this transverse shear, we are only considering the bending. And then we saw that principle of superposition, that we have a different type of the loadings. There may be axial load, there may be torsional loads, there may be pure bending, or combination of any of these loads. So we will calculate respectively sigmas and the tau, and then we add up all the sigmas in a particular xyz direction, and then we will add up all the tau in the particular plane x, y, y, z, or zx. This is what we have already learned in chapter 2. So we add up all this, and then we come up with a one sigmas and one tau value because of all different type of the loading. This is called law of superposition. And somewhere in the chapter 6 or 7, or on the later stage, we will deal with such problem in which we have different type of the loadings on a same member, and that will be causing it. So what the idea of this whole MOM lecture is, or the whole MOM subject, is that you must know what type of loading will be causing what type of stress, right? And what for that particular step, what are the what the specific expressions you are going to use, to calculate that particular stress value, so that you can have finally, by the end of the day, you can have the final complete state of stress for that particular object under different type of the loadings. So these are all loading. Axial loads are the load, a different type of load. Then you have the torsion. Then you have the moments that's causing bending. Then you have the transverse load that will be causing, in chapter 5, that will be causing a bending shear or the transverse shear. So these are different type of the loads, and you must have a very clear idea what type of load will be creating what type of the sex. Loads are always actions, and stresses are always the reactions, right? So you have to calculate what sort of action is there and what particular sort of reaction will be there, and then you plan accordingly how to deal with all this situation. So you add up all the sigmas, normal stress values, and you calculate all the taus, and you can calculate and you sum up all those taus and sigmas, and then you come up with the particular state of stress. Then we saw this one. We discussed that sum of all the forces about x-axis is 0. This is what we have already discussed today as well. My is again 0 because they are one about this y-axis. About this y-axis, this force is causing this way, and this force is causing this way turning about the y-axis. So they are again opposite to each other. So that's sum of all this will be 0. But mz will not be 0. This is what we have already discussed in detail, that that this particular compressive stress on above the neutral surface and neutral surface tensile forces neutral surface will be creating the moment about the z-axis in the same direction. So they are going to add up, and that will be mz, moment about z, will be causing equals to 0, and d is sigma. This is basically the f, and this is the y distance, that is basically this distance that is causing the moment, right? So then we discuss pure bending. This I would have already discussed, and then we have discussed the neutral planes, symmetric, and then we have discussed that in pure bending the parallel lines remains parallel to each other, and the vertical lines tilt towards each other. They remain no more parallel to each other, like you can see over here. They are no more parallel to each other, and they would have some intersection over here if I draw somewhere, so they will be intersecting on each other, right? So then we discuss neutral axis, and we define the neutral axis is the axis along which compression and tension is taking place, generally normal to the force. I mean, this is the force, and this is the normal plane, right? This is the force, and this is the normal place, right? So we have to see that how the force is coming, in which direction it is coming, and in which particular plane, it will be causing bending, right? So the plane about which that is called the neutral axis of that particular body, right? So these are so let's start today's chapter, today's part of the chapter, right? The first is called centroid, right? The first, we have already seen that if you discuss with qx and qy, that was the first moment of area about x-axis, and first moment of area about the y-axis, right? X-axis and y-axis. So we have already defined in chapter 3 as well, discussed in very much detail, so I am not going into that one. This first moment of area is used to calculate the centroid, right? Centroid is a very important information for us, because we have to calculate the stresses about this. So we have to know that where the centroid is. So centroid is y bar a equals to this first moment of area, and y bar is basically the location of the centroid. How we calculate it? Let's see that this is a particular shape over here, right? So what you do, first step is you take the reference axis. Reference axis over here, right? This is the reference axis. This is x-axis, this is x-axis, and this is y-axis, right? And second is you can place it anywhere, but in this particular case it is placed over here, where y is equal to 0 and x is equal to 0, and this is going in this direction, right? This is x-axis, this is y-axis, right? And then what you do, you divide this whole shape into different areas depending upon the shapes. Like in this particular case, you can see this is one shape, this is second shape, and this is third shape. So you calculate the area of that shape. For example, for this particular one, it is h1b1. For this one, it is h1b1. Uh, for this one, it is h2a2, and for this top one is h3b3. Now, y1, where is y1? Y1 is basically this one. This is the centroid location, y1. Supposingly, this is the centroid location, y1 over here. So y1 is half of the, because it is located in the center. So obviously centroid always located in the geometric center of that particular shape. So geometric center of this particular shape will be at, if this is h1 of this whole shape, this will be 0.5 of h1. Like this one, this a2 will be, this one a2 will be h1 plus 0.5 of h2. A3 will be a y bar 3 will be, sorry, this will be y1, this will be y1, this will be y2, and this will be y3, and y3 will be h1 plus h2 plus half of the h3, 0.5 of h3. And now we have this one and this area, so we can calculate the first moment of area by multiplying the area into the centroid. So you can calculate like this one, right? And if you want to calculate the centroid of whole shape, it will be y bar equals to sum of all the areas divided by sum of all the sum of all the first moment of areas divided by the sum of all the areas. So you will get the y bar of this particular shape, right? So about y-axis. So what you are going to do now, you have a shape, you will place your reference axis, you will calculate the areas, and you will divide the whole shape into different areas, and you will calculate the area of that particular shape, and then you will calculate the first moment of area into center. You will calculate the centroid, and then you will calculate the first moment of area of that particular, of each particular shape, and then you add up all the first moment of areas of the we add up all the first moment areas divided by the sum of all the areas in this particular case, and then you will end up with the y bar, and this y bar will be the centroid of this whole shape, right? Now come with the second point, that is this moment of inertia, that is called moment of inertia. This is the Ix, right? This is the second moment of area, or no, moment of inertia. Second moment of area or moment of inertia. This is what we have already seen. Ix is equal to y square dA, and you integrate it over the area, right? These are different shapes. For example, this is for the rectangle one, this is for the circular one, this is for the triangular one, right? So it is fixed. I mean, the formulas will be given to you. I mean, you don't need to worry about it. What sort of shape is there? Whatsoever shape is, you have a fixed formula over there, and you can calculate the I immediately from that expression. And here it is how calculated, because it is on the area y square dA. Y square dA is dy by dx. If it is if this is dy and this is dx, so area will be dy by dx. Y square will be the distance with reference to x-axis, right? And since we have that y square, so we can have a two integral limits, one in terms of the width and one in terms of the height, right? And when we will do the whole integration stuff, also we will come with bh cube and b cube h, right? So the difference between these two is you have to decide that on which axis, along which axis you are want to calculate the second moment of area, right? For example, if you have the x-axis, so the parameter along the x-axis is b, right? You are taking, this is the thumb rule. If you are taking Ix, moment of inertia about x-axis, so the parameter of the shape which is along the x-axis will come with a single power with respect to the parameter which is along the y-axis and its cubic power, like this one. So b, since b is along the x-axis and you are calculating I-axis, so b will come with the single power, and the rest other will become with the cube of that. When you are calculating IY, now we implement this methodology on the IY. IY is the parameter along the y-axis is h, so it will be coming with a single power, whereas b will be coming bh cube, right? So I'll just give, so this is how you can calculate the moment of inertia. Moment of inertia is somehow that gives you the stiffness of any body. If you, मैं यहाँ पे आपको एग्जांपल दूंगा कि कभी आपने देखा ये जो पानी के ऊपर लोगों ने अक्सर फटा रखा हुआ होता है, जिस पे आप गुजरते हो, सीढ़ियाँ हैं या ये जो मजदूर जिस वक्त काम कर रहे होते हैं, तो वो एक फटा रख के उस पे से गुजर रहे होते हैं ताकि वो स्लिप ना हो, ठीक है? वो किस तरह पड़ा हुआ होता है? वो बेसिकली इस तरह पड़ा होता है कि रेक्टेंगल शेप होती है, ठीक है, जिसका वाइडर एरिया जो है वो आपके गुजरने के लिए होता है, और स्मॉलर एरिया जो है वो आपका उसकी हाइट होती है, राइट? तो जिस वक्त आप उस पे से गुजरते हो तो इट फ्लेक्सेस, ठीक है? उसके अंदर वो बेसिकली उसके अंदर बेंडिंग आती है जिस वक्त आप उसके ऊपर से गुजरते हो, ठीक है? अब अगर मैं उसको वर्टिकल कर दूं, अब वो उसकी जो चौड़ाई वाली, जो चौड़ा हिस्सा था उसको मैं वर्टिकल कर दूं, तो अब बेसिकली क्या होगा? अब जो उसकी हाइट होगी वो वर्टिकली होगी, और जो उसकी विड्थ होगी, जो उसका चौड़ी साइड होगी, वो आपकी वर्टिकल आ जाएगी, ठीक है? अब जिस वक्त आप उसके ऊपर से गुजरोगे तो वो कभी भी बेंड नहीं होगा, ठीक है? मींस कि अब उसकी स्टिफनेस बढ़ गई है, ठीक है? अब क्या कर रहे हो? अब सिंपल ये कर रहे हो, फॉर एग्जांपल अगर ये वाली चीज जो है ये वाली चीज है जिसके ऊपर से ये फटा इस तरह पड़ा हुआ है, ठीक है, और आप इसके ऊपर से गुजर रहे हो, ठीक है, तो जिस वक्त आप इसके ऊपर से गुजरोगे तो इट विल बी BH³/12, राइट। और अब अगर मैंने इस फटे को इस तरह रख दिया और अब ये फटा इस तरह पड़ा हुआ है, ठीक है, और अब आप ऊपर से गुजर रहे हो, तो अब क्या हो रहा है, अब बेसिकली ये हो रहा है कि आपने जो उसकी बी थी उसको आपने एच में कन्वर्ट कर दिया, ठीक है, बी को आपने एच में कन्वर्ट कर दिया और एच जो है अब उसका बी है, तो नाउ यू विल कम ओवर एयर। क्या हुआ, बी पहले में सिंगल पावर थी, यहां पे बी क्यूबिक पावर है, राइट। So you have increased the moment of inertia cubic time than the Ix. So आपकी स्टिफनेस भी उसी लिहाज से बढ़ गई। अब जिस वक्त आप उसके ऊपर से गुजरोगे, उस फ्लैट फट्टे के ऊपर से गुजरोगे, ठीक है, जो कि वर्टिकली खड़ा हुआ है इंस्टेड ऑफ द हॉरिजॉन्टली, ठीक है, तो वो कभी भी बेंड नहीं होगा, बिकॉज यू हैव इंक्रीज दिस मोमेंट ऑफ एरिया। मोमेंट ऑफ एरिया उसका इंक्रीज होने की वजह से उसकी स्टिफनेस भी इंक्रीज हो गई है, ठीक है। इसी वजह से आपने पुराने घरों में देखा होगा, यू विल हैव टू सी दैट जो पुरानी घरों की छतें थी जो मिट्टी की बना करती थी उसमें शतीर लगा करते थे लकड़ी के। अभी भी जो आपके आई बीम्स लगते हैं, जो गर्डर्स लगते हैं, ठीक है, वो हमेशा वर्टिकली खड़े हुए होते हैं। उनकी हाइट ज्यादा होती है, उनकी विड्थ जो फ्रंट पे आपको नजर आ रही होती है विड्थ उसकी, वो कम होती है। वो इसी वजह से होती है ताकि जिस वक्त उसके ऊपर लोड आए तो उसकी स्टिफनेस मेंटेन रहे और वो हाई स्टिफनेस पे रहे ताकि किसी भी वजह से कोई उसमें बेंडिंग ना आ सके। सो मोमेंट ऑफ इनर्शिया का जो प्राइमरी ऑब्जेक्टिव है दैट इज यूज टू कैलकुलेट द used to calculate the stiffness of that particular object, right? Parallel axis theorem, that is another theorem. Generally you calculate I at IC at the centroid, right? So you calculate the center of the you can calculate the moment of inertia at the centroid, but sometimes it happens that you are not interested. For example, this is a shape, this is the center, this center is IC, right? You calculate that over here, this is the one. But I am interested somehow to calculate this over here. So what we'll do? This IC plus this is the D distance and area of this section, whatsoever that is. In this particular same, there will be no difference between the area over here and the area over here, right? And D is the distance between the centroid and that particular plane on which you are interested to calculate I. So this is called parallel axis theorem. IC will be you will use the expression of this, that is HB³/12, whatsoever that is you have just seen, plus D is the distance, and D square will be the square of the distance between these two centroid and the desired plane, and area will be the area of this cross section, right? So you will calculate in this way the I at any particular axis other than the centroid, right? So that is called parallel axis theorem, and you will frequently be using this parallel axis theorem somewhere in the next lectures while calculating the mathematics or the numerical, right? So here we stop for the time being, and then we will continue another lecture for our just let me see what the time is. It is 9:32, so probably it will be stop sharing. I'll stop sharing it, and then I'll come up with the second part of this lecture in my next lecture, right? So here I end my first part of the lecture.